Do you want to become an epic hacker? Do you want to know how to get infinite money or XP in any game, or teach your character how to fly when they clearly shouldn't be able to? Do you want to know how to turn this into this? Well, don't worry, I will guide you down the path of video game reverse engineering. Now, the game we will be violating today is Baldur's Gate Dark Alliance. You may have heard of Baldur's Gate 3. This is the older hack and slash version, essentially. Now, I hope no one will get mad at me because this game has a cheat menu built into it. So we're essentially going to be cheating without the cheat menu to show you how it's done. I also recommend you check out the game. It has an awesome soundtrack. Before we actually do anything, we need to understand how memory works at a low level. Normally when we count numbers, we operate in a base 10 system. So for example, we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But computers, they operate in ones and zeros. So this would be a base 2 system. And when we're looking at something like Cheat Engine, they're going to be operating in a base 16 system. So that means when we see something like an address, we're going to see letters like A, B, C, D, E, and F, which is the extra 6 onto this 10. So when you're counting and you see 1, 2, 3, it would go 9, A, B, C, D, E, F, 10. So as you can see, we're adding in a significant number of potential digits to shorten the visual length on something like an address. So we're going to have addresses that are represented like 0x, which means hexadecimal, and we can say 1, 2, 3, F, A, 6, 7, 1. And at this address, we're going to have 1 byte of memory stored at offset 0, and it's going to be something random like 0f, and we can have another byte at offset 1, and so forth. AA 1. Now what you see here are byte codes. So for example, FF would equal 255 in decimal, or 11111111 in binary. That's why I'm assuming another reason we use hexadecimal here, because it's super simple with byte codes. FF means the maximum amount that can be stored in 1 byte, and 00 is obviously all zeros. Now each address can store exactly 1 byte, so at this address we're storing this, for example, 0f, and then at 0x123FA672 we would be storing AA. So every address can store only 1 byte of memory. And when we store something like an int32 in a programming language, int 32 bits, that is 4 bytes. Because 8 times 4 is 32 bits, obviously. So that would be 4 addresses starting at something like this. And then since we know it's an int32, we would know implicitly to take the next 3 addresses into account when calculating this int32. And if you don't believe me, I have a programming calculator up here to see what the representations are. I type in FF, we see 11111111. That's 8 bits, 1 byte. And if we come over here, type in 9 plus 1, we get A plus 1, B, and so forth until we get 10. Int 32 number, so let's just type in 2 billion, I guess. 123, 123, 123. This is 4 bytes of memory, as we can see. 1 byte, 2 byte, 3 byte, 4 byte. Now the 3 tools you're going to need are a memory scanner, something like Cheat Engine or PINCE I'm going to be using in this tutorial, which is going to be pretty much exactly like Cheat Engine. So if you're on Windows, go ahead and grab Cheat Engine. Next thing we're going to need is ReClass.net. ReClass.net is an RTTI data structure dissection tool, I guess you could say. It's essentially a way to understand how an object is going to be represented in memory from a game. And the third thing you probably won't need for this video is the software reverse engineering framework Ghidra from the NSA, which is basically a static analysis tool for converting ones and zeros back into readable C++ code. This is not going to be in the scope of this video, but if you guys like this video, I can make another one covering Ghidra and how you can do static analysis. So hopping into our memory scanner here, we want to attach to a process and type in the name of our process. Now, after we've attached, we want to find the value, the current value of the thing we're looking for, and we're going to be looking for money in this case. So we're going to pick up some coins, see that the value is 1, go back to our memory scanner, search for an integer with the value of 1. Hit first scan. Now we're going to try and modify our money. Now we're at 3, and we're going to do next scan for 3. And we don't quite have it yet. So we can go modify our money again and do it one more time. Now we have 4, and we can type in 4 here, and we get our value, and we can just double click to modify this value. And we can set it to something like 100 just for testing real quick. Ensure that this is actually reflected in the game. As we can see, we have $100 now. So now we can go ahead and set it to something absurd like 1 million. And there you go. It really is that easy to cheat in some games, especially old single-player games like this. Now that we have our money, we can juice our character at the shopkeep. After testing our new gear, we can go ahead and continue with the experience hack. So same principle, we're going to kill some things, look at our experience, and then try to find this value in our memory scanner, which is 593. After we have this value, we are going to kill another thing and then see where the experience lies. 668, next scan. And here we have our experience. Now after we've done that, we can modify our experience, kill something to trigger the level up, and we see it works. So after we spend a couple points here, we can jack this up to the maximum. At this point, our character is pretty much a god, but what if the value we want to modify changes every time we relaunch the game? Something like health that we can't modify once and then it will stay forever. We need to keep getting that value every time. For this, we're going to need to create a pointer map so that we can find the same address regardless of when we attach our cheat engine. For this pointer scan, we're going to be using armor. So same method as before, we're going to unequip and re-equip our helmet, locate our armor value. Then we're going to right click on this and find what writes to this address. We see a couple of instructions have modified it, and the offset we're looking for here is 1DE, and the address for presumably our player object is stored in RAX. So at the value stored at RAX plus 1DE, we have our armor. And we can assume for now that the player is RAX. So we're going to enforce this pointer map to end in the offset 1DE, change the depth and the scan range, close the game, reopen it, and run the same exact scan, and then filter across those two pointer maps and ensure that we are getting to the right value both times. Then we can create a pointer using one of these values that has retained after the restart. And we can check after loading back into the game that the armor is the same. And if it's not, then we can switch to another pointer in the pointer map, another deep pointer, I should say, and then redefine the values. Now after we've got a consistent deep pointer, we can essentially just remove that last offset and grab that address, and then we have our player address that we can grab consistently. And now we're going to be putting this into ReClass to see what other values we can extract out of this player data structure. So if we grab that address, come into ReClass here, and put it in the left field, after we attach to the process, of course, we can add a bunch of bytes, and then we can start moving around and seeing how our character is affecting the values in here. And immediately we can see an X, Y, and Z representation for the floats up there at the top. So if we think that it's a 32-bit aligned data structure, we can obviously force everything in here to be hex 32. So now everything is offset by 4 bytes at a time and showing us 4 different interpretations of that 4 bytes of memory. These 3 offsets are clearly X, Y, and Z, and we can see that, and we can also modify it. If we modify the Z here, we will see our character instantly teleport up into the air. And we can go ahead with the same process as well. We can come over here and manually put in our armor because we've already found that and we know the offset is 1DE. And we can also figure out that our health is in here as well, which would have been really hard to find with just a traditional memory scanner. Now the real power of ReClass, in my opinion, is its ability to generate C++ code and all of the offsets for this data structure, so we can just simply copy paste this into our program we're going to design in a second to automatically grab these values. I also went ahead and found the Z velocity value that we're going to use in our C++ code in a moment. So for the final stretch here, we're going to be using something called libmem. It's a GitHub that I'll have linked in the description to modify process memory. Now, of course, we're going to copy paste our player data structure that we got from ReClass. And in our main function, we're going to find the process, ensure that it has actually been found. We're going to enumerate on the modules, grab the correct one, find the base address and its offset that we found in that pointer map, resolve the deep pointer, read the memory, and we can test this with our couts there. And then after we ensure that this is working, we can move on to a simple console application using ncurses. All this is essentially doing is checking if we press the spacebar key when this window is focused, and we're going to write to that Z velocity value. So as we see here, we can make our character airborne by pressing the spacebar key while it's focused over the console window. Now this is very simple, but it's to show you the possibilities of what's capable with these simple 4 tools. Now, this is what's known as an external cheat, but most advanced cheats rely on internal cheats, which means that it's injected through a shared library. This is most commonly known as a DLL injection. With these tools, you could also hook directly into the jump function, for example, and set this velocity there instead of having to rely on this janky external spacebar solution. If you enjoyed this video, make sure to let me know if you want to see more like it. I would be happy to do the Ghidra static analysis video.